Great observation. Okay, so thanks everybody for stopping in and coming to listen to Armando's master's thesis defense. Armando's been a ECSC, NOAA ECSC student for the past couple of years. The ECSC program, Environmental Cooperative Science Center, has funded his most of his research and has supported him here at DSU. Armando is going to be talking to you today about his research that was accomplished in Apalachicola Bay, Florida. Armando and several of my graduate students have been studying barrier islands, in the Apalachicola Bay, primarily as essentially asking how do these islands function as a resource, coastal resource, for migratory birds. The migratory bird stopover sites along the Gulf Coast, which Armando's going to explain in more detail in a moment, are really a significant international coastal resource in terms of the numbers of birds that stop along those barrier islands and refuel after crossing the Gulf of Mexico before they continue north to settle on the breeding grounds in the United States and Canada, and in a few cases in Siberia, if you can believe that. So they really are a significant, the barrier islands really do support a significant international resource. So Armando's going to be talking to you about that. Just a brief background on Armando. Armando started here in 2015, thanks. Started in 2015. He came to us after graduating with a BS in wildlife biology from Humboldt State University. He spent a significant amount of time researching birds in the tropics, in particular in the Amazon and I think Borneo, correct? Armando had great fortune to work with Tom Martin, who is a top avian ecologist. So Armando has worked with some of the best out there. So we were very excited to be able to bring Armando to DSU. So again, his research here at DSU was investigating barrier islands as resources for migrating birds, Apalachicola National Estuarine Research Reserve. And I guess with that, we'll hand it over to Armando.
All right, thanks for coming, everybody. I'm Armando. The title of my thesis is Migratory Songbird Resource Use for the Gulf Coast Barrier Islands, an annual cycle perspective. So the phenomenon we're talking about is migration. Migration is a seasonally predictable movement of individual or a population from one area to another. And it's usually in response to resource use or breeding or seasonal climatic shifts. And the amazing thing is that it occurs in a wide variety of taxonomic groups. Here you have a good sample of them. And even within a taxonomic group like the birds, you think of migration happening with flight. Of course, penguins fly. Penguins don't fly, penguins fly. So in general, avian migration occurs. They winter in sort of warmer tropical habitats and they breed up in the northern temperate habitats. And they choose a wide variety of pathways. So each one of these dots represents a mean of a species. So each one is a different species. You can see they all use different speeds, different routes. So it's a quite complex process. And being a person that studies birds at this day and age, it's amazing because we have this resource called eBird, which is a citizen science network where anybody can upload a sighting of a bird, what species it was, where it was, and sometimes what it was doing. And this is really caught on, and a lot of people provide eBird sightings. And so with this, you can build these amazing occurrence maps here where you can look phenologically, you can see what's going on, where the birds are going, and even what migration routes they're taking. So you're going to see here, the Mississippi River kind of fills in. And of course, with these massive data sets, you can also see what kind of impact we're having on these birds. So some of the big threats to birds are habitat loss, invasive species, and direct killing. Okay. So here, this aerial photo is Kent County. You can see it's extremely fragmented, which would limit connectivity of bird migration. You see this house sparrow competing with the tree sparrow. So the house sparrow is from Europe and it's been introduced as an invasive species. And then you've got cats, and cats are a big threat to bird populations. So here in the red are some estimates of individual bird deaths by the top 12 human causes. And you can see it's just an amazing number. This is a yearly value. This is how many birds we estimate are killed just from bird killing. And if you look at the trend over time, it's not looking very good. So here we got, okay, so we've got 6 different charts here, and the species, these 4-letter codes are different bird species, and they're grouped together by chart based on the behavior that their populations have taken. So highlighted in pink are some of the birds that we work with in the Hexture lab, and most of them are in that C box there. And you can see it looks like there was a kind of stable system going on where there's natural declines and high points, but then it sort of leveled off somewhere around 1980s. And in general, if you look at the end, which is 2000, right? This is 1970 to 2000. In general, the birds are not doing as well as they used to be doing. And for migrant birds, this is also the case, and it's often magnified for migrants because they just cover a vast geographic area. They visit several countries of varying socio-political atmospheres and different priorities as far as conservation. So for that reason, these are intercontinental resources. But when you think about these big movements as a global thing, it's incredibly daunting to think about. So I think it's better to just think about it piece by piece. So one site that we've identified, so we pointed out, is the northern Gulf of Mexico. So it's right here. A lot of Dr. Hexture's birds from his geolocator data have been going there, and so we identified that as a really interesting site that not too many people have even researched. So the thing about the Gulf of Mexico is the birds that are migrating from the tropics, they're coming up to North America. So they can this presents the biggest barrier for migration, the biggest expanse where the birds are not tied to land. So a lot of birds will go around this western route, going up the coast of Mexico and just taking it relatively easy. It's not very risky. Some birds will hop across the Yucatan, go to Cuba and Florida, which is a safer route. But some birds will just do a trans-Gulf migration, which is the riskiest one to do. And then they arrive on the Gulf Coast of Mexico. The Gulf Coast of Mexico contains about, the northern coast of the Gulf of Mexico contains about 50 barrier islands. And that's our study system, barrier islands. And barrier islands are these depositions of sand that are created by wave action and storm action, and they vary quite a lot in their structure, function, and form. So it can be anything from just a little sliver of sand that barely rises above the waves, or it can be a massive plateau of sand that slowly accrues vegetation, and in the end, it contains vast mature forests. Like this is St. Vincent Island, and it's just covered with really dense, nice, old forests. Okay. And so, in general, we think of migration as a budget between time and energy from the bird's perspective. And migration is composed of flight and stopovers. And when a bird is flying, it's constantly losing energy, right, which necessitates stopover. And when a bird is making a stopover, it's constantly losing time, which is a bad thing because the birds that arrive to their breeding sites often have the best choice of habitat. So stopping over has its negative side, but there's a potential to gain energy at stopovers too. So therefore, the value of a stopover site is a function of the energy acquired there. So is it worth it for birds to stop over at Gulf Coast barrier islands when they can just hop right across to the mainland and perhaps find better habitat? And how do we even evaluate this? Because once again, it occurs on this massive geographic scale. These are actual dates from this bird that has a geolocator on it. So it happens on a massive geographic scale in a very slim temporal window. So how do we even assess stopover use when they're visiting these areas for just a few hours, sometimes a few days, sometimes only a week? So the way I want to do it is stable isotope analysis. And A stable isotope is essentially just a normal atom. It's an atom that has an extra, or it has a different number of neutrons than the standard. For example, carbon has 12 neutrons. It's a nice balanced atom. And 98.9% of the carbon atoms on Earth are of that kind, but 1.1% are this carbon-13, stable isotope of carbon. And although it's at 1.1% of all the atoms are carbon-13, it exists in just about every biological tissue at varying degrees. And so because of that, it occurs in predictable ways. So for example, a certain species of plant might have the same amount of carbon-13 relative to carbon-12 as the other species of plants. So we call it, this is a biological marker that we call it isotopic signature. So the value of carbon-13 within that is called the isotopic signature. And people have used this to study birds. Here's an example. It's Pete Mara, who's one of the legendary bird biologists. He studied this winter habitat quality in Jamaica of American red stars. And he found that they've segregated into two broad habitat types, a wet mangrove forest and a dry scrub habitat. And so the mangrove habitat is considered to be the higher quality habitat. The scrub habitat, not so much, based on how quickly the birds refuel and what kind of food items they can have. And so once these birds arrived at New Hampshire, which is where they breed, he was able to he detected that the early migrants had larger amounts of fat. They were just in better condition because they arrived early. He also took blood from them, and the carbon signature in the blood identified them as being from the high quality mangrove habitat, whereas the birds that arrived later and were in poor condition tended to be in this dry scrubby habitat. So with the carbon signature, they were able to detect a carryover effect from a wintering cell. You can also detect diet and make inferences about diet. So Pearson fed these yellow-rumped warblers an isotopically consistent diet without any insects. And then he slowly, incrementally fed them insects and found a nice negative correlation. So in the y-axis there, that's what we call the isotopic signature. It's delta 13C is the notation we use. So there's a nice negative correlation with insects. Podlesak et al. He collected a bunch of different tissues that represented different time frames and was able to suggest that birds shift diet during fall migration. So some broad questions that I want to ask are, how does physical condition relate to resource use? Does resource use shift during stopover? Okay, so that'll be the next chapter. And the third chapter will be, how does the resource use of coastal barrier islands during stopover relate to other resource use during other phases of migration? So I want to put Apalachicola Bay, our study site, into the context of a yearly migration cycle. All right, chapter 2 is called An Assessment of Apalachicola Bay Barrier Islands and Stopover Sites for Migrant Songbirds using Breath Stabilized Analysis. All right, so I guess I should define what a stopover site is. It's a location that provides migrating organisms with the opportunity to rest and refuel. So here we've got red knot. It's a famous bird because it winters in austral South America as far down as Tierra del Fuego, and it breeds as far north as the Arctic Circle. So you're talking about the expanse of the globe that it migrates every year. And it can't just do this nonstop, so it has to stop, make stopovers. And one of the most prominent sites is here in Delaware Bay, where it gorges itself on the eggs of horseshoe crabs. And these eggs are rich in fat and protein, so that really powers their migration. The framework that I'll be using to talk about stopover habitats and how to evaluate them is Melman et al.'s. And he categorized them based on stopover quality and the duration and time that the bird is making stopover. So the first is the fire escape. These are just like you would use a fire escape as a human being. They're rarely visited, but without them, you would likely die. So here I've got a picture of the stair set on Machia Seal Island, in the eastern coast of Canada. And the lighthouse keeper was just sitting around. There was this massive storm. And all these birds, he just went out after the storm and found that it was just the lawn, everything was covered in warblers. So these birds were just taking refuge from the storm. And this could also just be a rock in the middle of the sea or a cruise ship where birds just show up to survive. The next level up is what he calls a convenience store. And this, there's some resources, it's not that great, but it's enough to, there's food items to consume to convert into fat and to convert into energy. This is Dog Island in Florida on the left side, and East Ship Island on the right side, which is a prominent stopover site. The best level, the highest quality level is a full service hotel, and you have every single habitat characteristic necessary to power migration available at these sites. So these are big, expansive habitats like the Great Smoky Mountains or bottomland hardwood forests. So the way I'm measuring stopover value is by assessing the condition of birds between captures. So if they increase their condition or decrease their condition, it says something about quality. And I'm also sampling resource use, and I'll do that by sampling the carbon dioxide of the breath from the birds. So the breath of the birds contains stable isotopes from consumed foods. And the convenient thing for me is that diet incorporation rates are known. So the time it takes for the stable isotopes from the food to be detectable in the breath. Pablo et al. Did this work with experimentally fed yellow-rumped warblers, and he found it to be 2 to 6 hours. So a bird can eat something, and within 2 hours, it's detectable in the breath. 2 to 6 hours, which is really good for stopover studies. So my objectives is to assess the Barrier Island stopover use with exhaled breath of birds, and also use standard morphometrics, which is a way to measure physical condition. And I also sampled arthropods to try to match the diet to breath isotopes. The study site is Apalachicola Bay, Florida, here in the northern Gulf Coast of Mexico. So we have the Apalachicola River that comes down and spills into Apalachicola Bay, which is surrounded by a series of barrier islands. This long, thin one is St. George Island, and that's what I consider a really typical barrier island. It goes parallel to the shore. It's long, has like one narrow strand of trees on it. It's inhabited by a lot of people. It's a touristic center. But just to the west of it is St. Vincent Island. And St. Vincent Island is a totally atypical barrier island. It's really large, it's triangular shaped, and most importantly, it's got an interior, which doesn't happen on barrier islands very often. And the interior, you can see there, those little black dots on the eastern side of the island, those are really massive lake systems. So it's a really good, big habitat. Here's one of the habitat types you can find there, these really nice freshwater inundated forests where crocodiles have to live in. And then you've got these dry scrub oak habitats. So it's like this weird mixture of tropical and subtropical, and you got these spooky Spanish moths hanging off. And it's just such an awesome habitat type. And then, okay, so this is looking from the Gulf of Mexico. This is the river mouth. So in St. Vincent is a big enough barrier island that has a self-sustained river. And it's an excellent place to go fishing. So the birds are flying across the Gulf of Mexico, and the first thing they experience are these pine flatwoods. And the birds come down and they go into what we call the exploratory phase, where they just hop around the tops of the trees and try to figure things out. And then they eventually siphon through the different habitat types, what they prefer, maybe. And eventually they fall into our mist nets. And mist nets are just these, they're usually about 12-meter long. They're made of thin monofilament, so when you look at it straight on, you really can't see it. It blends in with the foliage perfectly. And so the bird does like what my hand is doing there, flies in, hits the net, it falls down like a little warbler down there in the corner, and it gets stuck there. And we pull it out like Melanie's pulling out this green heron, and put it into these white bags in the back of my trousers. And we take it back to the banding station. The first thing we do is we apply this aluminum band to it, so if we capture it again, we know that we're capturing the same individual. If somebody in Minnesota or something captures it, they can say, "Hey, we caught your bird," and we get really cool data when that happens. We determine the sex and the age of the bird, mostly from plumage at that point. We score the condition of the bird by scoring the fat and the muscle from 0 to about 5, sometimes more. And so 0 is, of course, the bird has no fat. And so we can blow on the bird, on the feathers, and look into its skin. And the skin is translucent. So you can see inside and see this like yellowish colored fat. And measure the wing, we take the mass, and I collect breath from the birds. And so this is my breath collection apparatus. So I pump in ambient air with this bicycle pump, which is working. I pump in ambient air, and of course ambient air has carbon-13 in it, so I don't want to measure the carbon-13 because, I mean, that's not the point. So I have to remove the carbon-13, and as it goes, the air goes through here, and it goes into this ascaret trap. And ascarite is sodium hydroxide, and sodium hydroxide is a highly aggressive carbon scrubber. So any carbon dioxide that goes into that ascarite trap is basically absorbed by the ascarite. So the resulting air that comes out of that top tube is free of carbon. And I have the bird inside of the chamber and all the valves are open, and I just flush some air through it to remove the carbon. And then I close all the stopcocks, and the bird sits inside of there for about 4 minutes in this holder. And all the while I'm really monitoring and making sure it's okay. And when 4 minutes are up, I have this needle sticking up at the top there. It's a broadhead needle. I uncap that, and I have this exotainer vial, which is it has a soft septum cap that's semi-permeable. And inside it's at negative pressure, so that when you pop it onto the needle, it just sucks in a 12 milliliter sample. And then that's it. And then you have this sample. It doesn't leave the vial. And then I just send it to UC Davis Stable Isotope Facility, and they run mass spectrometry on it. And they send you back delta 13C values, which is the amount of carbon 13 in your sample divided by the carbon 13 of a standard, which is just pure limestone. Subtract 1, multiply by 1,000 to get into parts per 1,000. And this results in a negative number, but that doesn't mean it's a negative value, it just means it's over a few decimal places. My study species, here they are. So great-cheeked thrush is a bird that breeds in the northern boreal forests. And it winters down in the Amazon forest. So that's a massive distance. It's an omnivore, so it eats insects or fruit depending on what's available and depending on where it's at. Indigo bunting, as you can see with its huge bill, it's a bit of a seed eater, and it's typical of mesic, brushy, dry habitats. It breeds in eastern North America and winters in Central America. Northern water thrush, like its name implies, is an aquatic specialist. You can find it in rivers and wetlands where it breeds in the northern boreal forest, and it winters down in Central America and northern South America. So I also put out some pitfall traps, and I established these in a kind of a wet site and a more upland site. So a pine forest site, and then it's a big puddle near our banding station. And I did this because Fry found a nice bimodal distribution of carbon signatures. So the birds were either a C3 pathway or a C4 pathway, which is a vastly different carbon signature. So I thought maybe I could do the same thing. And a little about this island sampling scheme. In 2015, we alternated between St. George Island and St. Vincent because we wanted to try to sample both at the same time. But that was logistically really challenging. We had to barge the truck on and organize everything and go to the grocery store a lot. And so 2016, we just focused on St. Vincent Island. Statistical analysis, I kept it pretty simple. I just did bandwidth and U-test and t-test, and I did some correlations. Okay, so the results. The important thing here that I just want to highlight is my sample sizes. So in general, 2015 was a better year, especially for the great-cheeked thrush. And this sample size, it's not the best, but that's pretty normal for birds, and it's actually better than the only other study that uses this methodology. So for northern water thrush, I compared the island data, St. George and St. Vincent, and there was nothing really, no difference. I just pulled all the data together. And in 2016, we just studied St. Vincent Island. Okay. So on the y-axis, you have the carbon signature. And remember, the carbon signature is an index for resource use. And it uses a FAT score. So for example, let's look at 2015 and the 0 FAT score. The carbon signature is all over the place, okay? So there's not much of a pattern here. You can almost see a bit of a correlation going on, but it's not really there, and it's pretty weak. The broad signatures between 2015 and 2016 were slightly different. So a more negative carbon signature is indicative of a moisture, wetter habitat. And so this makes sense because 2016 was an El Nino year, so it experienced more precipitation that year. So with the birds that were subsequently recaptured, which we had 6 of them, the birds that were not recaptured, we had 15. The birds that were recaptured later on initially had a smaller mass, and the other birds had a larger mass, which suggests that maybe because they had a small mass, they stuck around to increase their physical condition. With those birds that we did recapture, when you look at the overall initial capture versus the final capture, it was not significantly different. But I think the more telling thing is the range. So in the initial capture, they're using a lot of different resources. Okay? With the final capture, it really collapses down. We suggest that they're really honing in on something more specific. The minimum stopover duration for water thrushes was 1 to 6 days. So the one bird that stayed 6 days gained 3.3 grams, which is 25% of its original mass, which is it's pretty impressive. Indigo bunting, 2015, they're really all over the place. And so a little bit about the C3 versus C4 pathway. C4 pathways are associated with mesic dried scrubby habitats, and that would be up in the -20 range and above. And down low is the C4, which is more typical of like the water thrush would be there. So this is pretty interesting because this bird is associated with mesic habitats, and yet it's shown that it's not doing that in Florida. The gray-cheeked thrush, the most interesting result from this was that the carbon signature changed as the date of capture progressed. So what does this mean? Like, is there a resource shift going on? That's kind of the first thing I thought. So talk about that in a second. The stopover, we had only 2 thrushes that made a stopover. One of the birds was captured 3 times in one day. The other bird was captured the second day. So there was not much mass or change in breath signature. So a little physical, little difference in the physical condition. With the arthropod sample, I identified them to the order, and I found that I ran a crucible bolus test on these, and there was really no significant difference between all of them, which is unfortunate. That's all right. And then I compared the upland and the wetland site, and they were also similar in the terms of carbon signature. So what I gathered from the breath signature was that it varies by species and by date of capture. And in general, it doesn't vary by physical condition, which is a little bit surprising to me. I thought maybe it might be related. So with the northern water thrushes, recaptured birds gained mass, fat, and muscle during stopover, and yet they maintained a constant carbon signature. So this suggests no diet shifting. And the threshold I'm using for diet shifting is 2 parts per 1,000, which is based on an experimental feeding of another warbler species. And so they did not pass that threshold. So this is, again, the initial capture, this is the final capture, and it suggests that they're using the same resource. And I think that same resource that they're using throughout their tenure at the stopover site are just these inundated forests, these really wet habitats. And I think that's a really good habitat for northern water thrushes. This is what they're associated with on the breeding grounds and on the wintering grounds. So I think this stopover site is probably a full service hotel. It really goes in line with their foraging strategies. They stay low in wet habitats and forage on aquatic insects. And also, so this data here is from a wintering site in Venezuela for northern water thrushes. And they found that the higher quality habitat was the wetter site, the wet mangrove sites, because they gained fat and just increased physical condition at a faster rate in the wetter habitat. And my sample is from Apalachicola. We're also within this range. So that's one reason to think that it is a high quality habitat. Apalachicola is. And also it suggests that there was a lot of competition going on for this habitat. And while I didn't measure competition and territoriality, just anecdotally, we often experience sort of fights, territorial fights going on. You'd hear a northern water thrush chip. It's like a really punctuating chip sound just in the forest, and then you would hear another one going on over here, and then chip and chip, and they would get together, and eventually there'd be some kind of rustling, and there'd be a fight that ensued, and sometimes the water thrush would end up in the net. So I didn't measure this, but this suggests that it's a high quality habitat. If they're being territorial at a stopover site, which I should mention, that's very rare for birds to be territorial at a stopover site. But they are, so this is a high quality site. The insects, there was little variation between the orders. I was hoping that I'd be able to identify what order the water thrush are kind of honing in on, but that didn't happen. And it did happen for fry, so I'm not sure if maybe my sampling was a little bit off, but I think it has to do with the fact that the topography of St. Vincent Island is kind of this dune swale topography. So you can walk across the island, like you can walk 100 meters and be in 3 or 4 different habitat types. The turnover is so fast. So I think maybe that would cloud up any differences that we find between habitats. With the indigo buntings, I mentioned that they're C4 specialists on their wintering and breeding grounds, these dry mesic habitats. And some of them were reflective of that at the top there in the pink. But if you've been to this island, you know there aren't any dry like mesic grasslands, right? It's like a subtropical, very moist, very humid area. So I wonder what's going on with that. Even though most of these birds were down in the C4 range, there are a few that were up there, and I think that has to do with bird feeders. The people in St. George really like to feed their birds, and I think some of the birds were just eating birdseed, which is all right. That's also a resource, so good for them. The gray cheek thrush, the signature varied with the date of capture, right? Pretty good. So the initial thing you think of is that some kind of resource shift was happening to cause this, but the fact it didn't happen for northern water thrush, and I would imagine that this omnivorous bird, the gray cheek thrush, would kind of do the same thing as a water thrush would do. But this relationship didn't happen in the water thrush. However, it did happen in another Cathar's, bird of the Cathar's genus, in theory down here. So what's going on? But you know, if you take a breath signature of a bird that's been fasting, you still get a breath signature. You still get something. So really the right way to talk about what you get from the breath signature is you get a measure of the substrate metabolism. The substrate can be a diet source, and it can also be the internal substrate, the body of the bird. If the bird is fasting itself, it could be reflecting its internal combustion of its own body. But of course, this would be, you could tell this because the signature would be much more enriched, much more positive. So here's, this is Kent Hatch, and he measured the breath of doves. He fed them, so we're looking at these open circles here. So he fed them this wheat-based food that's a C4 food. And over time, at about 50 hours, they kind of got to the stable area. And then he took half of them off of it, just fasted them, and saw that they immediately increased to that upper level. So I think that could be happening with these birds as well. Okay, so here's the same gray cheek thrush correlation. And I've overlaid the northern water thrush means and range. And so I think some of the birds are definitely doing what the water thrushes are doing. They're foraging on probably the same food source. But I think these intermediate birds might be foraging as well, but they're probably also combusting their internal substrates. I think these birds are definitely just fasting and just not doing that great. But of course, I mentioned the breath signature was not related to physical conditions. So you would expect these birds are not doing well if they're fasting and things like that, that you'd be able to tell in the fat score. The fat score should be 0, and the muscle score should be like 1 or 0. But I think there's an alternative mechanism. That's a different energy source in fat, and it's glycogen. So a little bit about fasting metabolism. The firing order at which energy sources are combusted is first it's glycogen, which is a carbohydrate, then it's the lipids, so like the fat, then it's protein, so you would see that in the pectoral muscle of the bird. And that's convenient because glycogen has a very high energy to mass ratio, although not as much as fat, but pretty high. And also it's great because it preserves fat and muscle, and fat and muscle are the real mechanism that drives migration. These are the physical components. It's a sustainable fuel in the lipids, and it's the machinery in the pectoral muscle. So if glycogen burns off first, then that's extremely convenient. So Young and Moore did find that fat stores negatively correlated with the date of capture. So it's kind of what I was expecting would happen. And one of their hypotheses was that late migrants deposited less fat than early migrants before crossing the Gulf. So I think this could apply to glycogen as well. So late migrants deposited less glycogen than early migrants before crossing the Gulf. And glycogen is a quickly renewable source. It burns off quickly, but it's acquired really quickly as well. And I think one of the main sources that comes from is fruit. So Nick Bailey runs a banding station in the Santa Marta Mountains in Colombia. And he saw that these birds, they were showing up as prominent stopover sites, gray cheek thrushes, and they were foraging on a lot of fruit, just gorging themselves on fruit. And early birds kind of fueled slowly. They took their time and just ate a lot of stuff and had larger fat scores. Whereas later birds showed up and they found the fruit is more depleted of increased competition. So they try to fuel more quickly as a attempt to catch up. So I think fruit could cause the I think fruit could be the glycogen that these birds are burning off. So my kind of summary of that hypothesis that I have is stable isotope signature from the exhaled breath of the late arriving gray-cheeked thrushes likely reflects exhausted glycogen reserves. And I think that comes from a fruit source. And I think this could explain why they had an enriched carbon signature towards the end, the late birds, and yet they didn't show any signs of physical stress. Okay, so this is chapter 3. It's called The Use of Stable Isotope Analysis to Infer the Resource Use of Songbirds at a Gulf Coast Barrier Island, a Full Annual Cycle Approach. Okay, so now I'm going to kind of put Apalachicola Bay into the context of its entire migration cycle at 31. Okay. So we know a lot about what's going on in the breeding grounds and the wintering grounds because these are stationary periods in the bird's life. You can go to any territory and you expect to find a certain individual and you can easily observe what it's eating or what kind of behavior it's doing. But at migration stopover sites, we don't really know what's going on. We think that, well, the ideal situation is the bird would arrive at this unknown site and forage on an optimum food source to power its migration. Alternatively, birds can switch diets, which is another tactic toward migration. Finally, a bird can just forego stopover altogether and just continue going. But how do we evaluate stopovers resource use? Well, I think we can do this by looking at how they use resources on their breeding grounds and on their wintering grounds with a yardstick approach. So if we use the breeding grounds and wintering grounds as a standard, we see how far the stopover site deviates from those. But of course, that relies on having resource use from the breeding grounds and the wintering grounds, which is difficult, but we can do it with the isotopic clock model. So this posits that the time of food consumption can be estimated by sampling tissues and knowing the diet tissue turnover rate. So I alluded to this with the breath. I said the breath can be detected within 2 to 6 hours. Well, this is true for almost every tissue, and every tissue has a different tissue turnover rate. And some of these are well known in the literature. For example, the feathers of the bird. When a bird is done breeding on its spring breeding site, it molts its tail feather and regrows its tail feather. And the food that it consumes at the breeding site is used to construct the tail feather. And accordingly, the stable isotopes from those foods are then stored in the tail feather, and the tail feather is rendered inert. And so wherever the bird flies, it's carrying isotopes from the breeding site. So if you capture a bird today, and you take a claw, for example, the stable isotopes reflect the past 2 to 5 months, okay? With the red blood cells, they reflect the past 11 to 14 days, the plasma 9 to 25 hours, and the breath 2 to 6 hours. And this comes from lab trials from other researchers. So, because these birds are migratory, not only do the different tissues reflect different time frames, they also reflect different phases of migration. Okay? So in red here, I have the non-migratory phases, the flight feathers and the claws, and I have the migratory tissue, the tissues that represent the migratory phases. It's breath, plasma, and red blood cell. And so that circle next to where it says breath, that's where we collected all these tissues. And so from that point of view, this model, I think, is valid. So from that point of view, the claws represent the wintering phase. The red blood cells represent the early migration phase. The plasma represents the recent stopover site. The breath is the current stopover site. And flight feathers is the previous breeding season. Okay, so this is just a hypothetical model. And we can assess diet shifts between all of these by Podolsk's threshold, which is 2 parts per thousand. So if there's more than 2 parts per thousand difference between these tissues, we can say there's been a diet shift. If there's not, we can't really say that. And so we did the same methodology for this, except we collected feathers, claws, red blood cells, plasma, and breath. And the great thing about these is that they're non-destructive, so we just release the bird afterwards. With a tail feather, you just pluck one of the central feathers out and put it in an envelope. The claw, you just clip the end, avoiding the blood vessel, and then you you poke the bird in the brachial vein, and the blood beads up, and you take a little sample with a capillary tube. Then you put it into, then you centrifuge that sample down, and it splits it into the plasma and the blood. And the convenient thing about that is that those are two different time frames from one sample. So that's really fantastic. And I use the same breath methodology as the previous chapter. Okay, so I had to wash the oils off of the claws and the feathers, right, because they have their own carbon signatures. So you have to purify them by washing them in a powerful detergent, and then baking them, and then washing them in chloroform methanol solution to wash off the detergent. And you repeat this a few times, and then you have a purified sample. And I sent these to the Colorado Plateau Stable Isotope Lab at University of Northern Arizona for mass spectrometry. And my statistical analysis, I just use a one-way ANOVA between the different tissues to see if there's a difference. And I use a Tukey on a significant difference test. That's a Ronald Fisher and with a spectacles and John Tukey. So my results are essentially that I found evidence of diet shifting in 2 of the species, and I found that 1 species did not diet shift. Probably not. Okay, so these are this is the carbon signatures for the gray cheek thrush. So going across the bottom, we've got feather, claw, red blood cell, plasma, and breath. Once again, that describes the breeding habitat, respectively. The breeding habitat, the wintering habitat, the early migration stopover habitat, the most recent stopover habitat, and the breath represents the current stopover site, Appalachian Corridor. The amazing thing to me, at least, was that the wintering site and the breeding site, the first 2 were essentially the same thing. But then as migration commences, they use different food sources, different resources. And here's the nitrogen, and nitrogen was similar across with the exception of feather. So nitrogen describes more of what's going on with the protein. So it seems like they're using a similar protein base. And here we have carbon and nitrogen plotted together. And this kind of tells you about the trophic positioning in a relative matter. So if you look at feather and claw, which represents the breeding and the wintering sites, they're really clumped together up there. But with the red blood cell and the plasma, the migration tissues, it's just all over the place, which is kind of expected for an omnivorous bird. With the indigo bunting, the breeding and the wintering tissues, the first 2 there, were also pretty similar. And specifically, they're both in the C4 range. They're both clearly in the mesic dry scrubby habitat, which is really expected. But as migration commences, they use other forms of carbon as well. And nitrogen was similar across the board between all of the tissues. So when we plot the carbon and the nitrogen together, you can kind of see that the nitrogen and around 6 parts per thousand, there's kind of a straight line up there. But again, the feather and the claw, the blue and the purple, they're all kind of clustered around each other. With the northern water thrush, there was no significant difference between any of these. Which suggests they're using similar carbon resources at each site. And this is 2016. I think that there was a slight difference here, but it wasn't biologically significant with the 2 parts per thousand. Statistically, it was. Breath was different from claw. And the nitrogen was identical across statistically and biologically, and same with 2016. And when you plot these together, you kind of see this big mess, but really it's like a nice controlled mess. Everything is close together. Everything, there's really no pattern. Everything is just everywhere, which suggests that all of these different phases of migration is using a similar resource. So about the non-migratory phases. Okay, so here I have a picture on the left side of the boreal forest, right? And here on the right side, I've got the Amazon forest. And this is the breeding site and the wintering site of the gray cheek thrush. So they're geographically as far as the bird goes during its entire life. And yet they were isotopically indistinguishable from one another, both with the carbon and the nitrogen. So that suggests that they're just using the same sort of resources that, at least isotopically, they're indistinguishable. Same thing with the indigo bunting. Its northern breeding sites in grasslands in North America, as well as grasslands in Central America, geographically distant, but isotopically they're similar. And for the northern water thrush, is boreal wetlands on the left side and mangroves in South America on the right side. they were also isotopically indistinguishable, but of course, really far from each other. So those are the non-migratory tissues in the red, the flight feather and the claws. They were not different from each other. There was a little more variation with the breath and the plasma and the red blood cell, the migratory tissues. Gray-cheeked thrush and indigo bunting did show a resource shift. And I suggest that this is an actual diet shift. They're shifting diet sources. And I think that because the tendency was that they all went, they decreased negatively, right? So that really suggests, so I mean this because this suggests that they're not fasting. If they're fasting, it would increase. Now you can see there in the gray-cheeked thrush, I think there are some individuals that are fasting. That's really enriched, just a few of them. But in general, they seem to be switching diets. With the northern water thrush, there was no dramatic or significant diet shift throughout the annual cycle. And this is kind of expected. I mean, this is what they do on their breeding and wintering sites. They use aquatic insects or insects associated with water at both sites. But I think this research is the first to show that their specialist lifestyle extends to their migration stopover sites as well. And I think for that reason, St. Vincent Island is placed well into the context of its entire migration cycle. It's a high-quality habitat similar to other high-quality sites based on the carbon signature. Its Apalachicola Bay is diverse and underdeveloped, and in particular, St. Vincent Island, it's totally uninhabited. There's nobody who lives there. It's relatively undisturbed, and it's big and massive and beautiful. And I think it's a high-quality site because birds gain fat, mass, and muscle while stopping over there and using a consistent resource that suggests it's high-quality habitat. We experienced some competition going on, and it's similar isotopically to other sites visited across the annual cycle. So all these reasons, I think this is a very high-quality site. I think it's definitely in the full-service hotel of Norman's framework. And especially because freshwater wetlands are extremely rare, and this has an abundance of them. So I think we should preserve those if we can. This is the first study to track intra-individual stable isotope analysis of spring migrants. There's only one other study that did this for fall migrants, and so this is the first. And it highlights not only landscape connectivity, which is what geolocators do, but with this, we're talking about resource connectivity. So how resource shifting changes over time and over geographic space. And so stable isotope analysis is kind of a magical tool that's not precise. You can't identify the species which the bird is eating. You can't identify the exact positioning or the exact time when it is. But as a relative index, I think it's incredibly powerful. And it does away with the problem of scale, of looking at these birds on geographic scales in slim temporal windows. And it's just incredibly convenient that we have this tool. And I think when it's used properly, it can really inform conservation. Okay, with that, I want to thank Megan Lamb and Rebecca Bernard from the Apalachicola National Estuarine Research Reserve for the logistical support down there. Bradley Smith and John Murphy, who work with the U.S. Fish and Wildlife Service on St. Vincent Island for expertise. Carol Brown for logistical support from Friends of St. Vincent Island. My committee, Christopher Heckscher, Kevin Bolanek, Sabrina McGarry, and Rich Procheski. The Heckscher Lab, Dr. Laura Lester, Alan Idle, Melanie Mancuso, and David Mendes, who work down in Florida with me. And I want to thank my funding source, which is the NOAA Environmental Cooperative Science Center, for funding this. Yeah. Now I'll say thanks and take questions. Okay.
You said that you use wheat as a seafood source in experiment. Wheat as a seafood.
Yeah, Podlesac used wheat as a C4, and they used oats as the C3.
Yeah, but wheat is a C3.
Really?
Yeah, wheat and I saw corn. That corn is a C4.
Sorry, I'm trying to find this later. Okay, I was under the impression that wheat was a C3.
Yeah, it's a corn. Corn is a C4.
Corn, yeah, corn is a C4.
Yeah.
And wheat is a C3.
Yeah.
Oh, I'm sorry, I meant to say C3.
Okay.
Okay. to say about that. Okay. Thanks.
And the other thing, the carbon, the delta protein carbon for seafood plants is close, and the average is about minus 14. For seafood plants, it's like average around minus 28. So I can see why, because they would definitely like only one species.
Right, yeah.
So you can see the legs.
Yeah, there's
It looks good.
mixing up. Yeah, like,
Armando, great talk. 2015, 2016 were big differences in years, right? In terms of water, right? Rainfall.
Yeah.
So did you see, were there changes in the amount of standing water around in terms of available freshwater habitat for the birds?
you know, I can't say that I noticed that exactly, but I imagine there was. But yeah, I didn't just notice that. There was tons of fresh water. I guess I'm kind of having trouble remembering how it looked like in 2015.
Yeah.
But in 2016, I mean, our nets were set up on this berm, and on either side they're just filled with puddles. I mean, there would be alligators sitting underneath our nets and just crossing over from one puddle to the other. So it was very wet. This is just an old berm that was constructed as an old road that's no longer used on St. Vincent Island. And so, but otherwise, the whole thing would be just super wet.
And you didn't see any sign of that, though. I mean, when you looked at your stable isotope analysis, did you see? I mean, I didn't see anything that was. And I'm thinking about the rush or the.
Yeah. So actually, I did kind of detect a difference between 2015 and 2016. Is what you're talking about?
No, is it the water rush?
Yeah.
Yeah. Okay. So I must have missed this one slide. Okay.
Yeah. So it was. Yeah, the breath signatures were slightly more depleted in 2016, which was the wetter year.
Is that significant?
No, it's not significant. No.
Yeah, did you notice any differences between the two different islands? Because I'm wondering if just the fact that half of these birds were on St. George, if that can account for the difference here.
Yeah, so I talked about that. So I tested the northern water thrushes of the St. Vincent Island and St. George Island, and there was no difference. So with indigo bunting, there was a difference.
Okay.
So it depends on the species. But again, I think the indigo bunting was more of a result of bird feeders rather than natural island. So part of that. Yeah, that's the one.
So when you did your insect trapping, you set the fall traps exclusively, right?
Mm-hmm.
So you're going to be getting a really different insect fauna. I mean, a lot of them being predatory, like rabbit beetles and stuff, than you would if you were doing, say, spook netting.
Yeah, so the reason I did pitfall trapping is because both of my insectivorous birds are ground foragers. So that's why I just restricted to the bottom. I guess it would have been a good idea to sweep that in the lower species, but I just, yeah, I wanted to do pitfall traps because it was easy.
Can't quite go back down and do it, but for future research.
Yeah.
Those two species do forage in the leaf litter. They're flipping over leaves.
Yeah, so they
Right,
don't often-
but did they get at all into the grasses or the, the low-hanging vegetation?
I mean, they do, but in general, they're classic thrush will just hop around, like lift up a leaf, eat something, and keep going with it. So, so I think they would primarily forage on the ground, but they forage on or near the ground. Yeah.
I have a question about the chloroform and the methanol.
Okay.
They have a stable isotopic signature as well.
Yeah.
So did that,
Yeah, so the reason that's probably not an issue is because chloroform and methanol are extremely volatile, so it just completely evaporates. And then after that step, I also wash it in water and then bake it.
Yeah, those are the little species of the bluebird.
Yeah, the indigo bunting.
Yeah, and you go at the feather. Those are hard. Those are really low
Signature?
signature. And I was wondering who I was. That was beautiful there, but that part of them, not here. In another, one of the ones who was there.
Let's see. Not sure which one. think this is the only one I presented for the bunting. Is it a different species?
Yeah, it was all different species was there. And most of them. Where you did the bird, where you had the seafoods, is.
Oh, okay, I got it. It's, I think it's the same chart. This one?
Yeah, that was the bird, but the secretary had a, for the feathers, they, and different.
Ah, I got you. Yeah, so what were you putting? This one?
Yes, that one. You see the feather there?
Yeah.
First one, you see how far they.
Oh, yeah, that's,
Up there?
yeah, that's crazy. I don't know.
Yeah, it's fascinating that, because that means that the feather is being fed by that the material comes from seafood plant.
Yeah, so it's either that or there was an issue with that sample. I'm not exactly sure. I don't really know how to interpret it.
It's amazing.
But it's an extreme outlier, I would say. I mean, the range is, it's really tight.
Yeah, the core two is in similar range, it really has a bigger variation.
Yeah.
What's your sample size on them, on those feathers?
So 20. Most of these are 20.
So where would you think those buntings are breeding? I mean, that's from the breeding ground, the feather.
Yeah. I mean,
Any idea?
there's no way I could, just because the indigo bunting have such a massive range. You can't tell that from carbon. If it was hydrogen, you could figure out the latitude, more or less. But I can say that they're using extremely dry and basic habitats, typically CBD.
And probably those 20 individuals are not breeding together.
Yeah,
So,
no, I don't think so.
and it's still pretty tight.
Yeah.
So it's kind of interesting.
Yeah.
I mean, that probably represents a pretty broad geographic area,
I think so.
those individuals.
Yeah. Yeah, and I mean, the gray cheek thrush was also really tight as well, which really just suggests that, yeah, they're all using a very common resource to feed through.
Not really switching around. I mean,
There might be
they're
some-
probably consistently feeding on the same type of resource.
Probably.
Yeah. So I have a question. So towards the end of your talk there, when you were concluding things, you mentioned that, you know, this is good data that can inform conservation, right? Can you give us an example of how a conservationist or a land manager might use this data? I mean, if you're managing land, if you're NOAA or if you're someone at the near site and you're managing land down along Apalachicola, how can this data possibly be meaningful? I mean, how would they apply your results?
Well, there's essentially not much known about stopover in general. So I think any information that we can provide is really beneficial. But this in particular, you know, it allows you to gauge the deviation from these wintering and breeding sites and how far the resource use deviates. And if you're saying that it doesn't deviate very much, that really suggests it's a high quality site. And I think in addition, one way you can increase precision with this stabilized analysis is by coupling this with geolocators. So you can actually get an exact site of where these things are incorporated. With this, you're kind of just guessing where it is. You know the relative, you know that it's breeding at this time of the year or it's wintering at this time of the year. So with geolocators, you can increase precision. So I think with all this, you're informing about resource connectivity. Not so much landscape connectivity, but this really important aspect that shows how birds can, you know, what kind of resources are available.
But why should a land manager, why should someone working down there care? I mean, what?
If they want to preserve the birds, well, this is just a way to suggest that St. Vincent Island falls in line with other stopover sites. It's a way to say, if you look at this and if you look at stuff that's published from the wintering sites and breeding sites with stable isotopes, it's similar across the board. And I don't think this would happen at every single stopover site. Okay. I think if you went to Texas, there was one study where they went to Texas and wild thrushes showed up and just immediately left because there was nothing floating there. If I did that study in Texas, I don't think I would get these results. So I think the fact that there was so much homogeneity between the tissues just really suggests that it's a high quality site. It's got wetlands and it's got lots of wetland insects, which is what the bird uses to.
So, I mean, essentially, you're placing a conservation value on the wetlands at St. Vincent Island,
Correct.
in the Apalachicola Bay area.
Yeah, for the water pressure, yeah.
Any other questions for Armando?
Just taking it a step further, so right now, the Army Corps of Engineers and the federal government and the Supreme Court are all fighting over what they're gonna do with the Apalachicola River. The water coming down the Apalachicola River. Have you been keeping abreast of that at all, and or could that impact your study or the value of these barrier islands?
Yeah, I haven't really been keeping up with that, but I think, yeah, anything could affect these big islands. The important thing about our study site is there's a lot of freshwater wetlands. If you have an increase in sea level rise, either from climate change or from the river flowing in, you have increased salinization of these sites, and you have habitat conversion. So I think, yeah, I don't know what it used to be like, but I think it's functioning really well now, and maybe it wouldn't do that much damage to increase the water flow or whatever they're planning on doing, but I think it could definitely affect what's going on in St. Vincent. I think barrier islands are very tenuous, and we should be careful what we do with them. And I think historically we've been thinking of barrier islands as kind of this afterthought, but a place like St. Vincent Island is a very high quality habitat that we should try to preserve as well as we can. So I think it should definitely be considered in this type of plan.
I can tell you, if you guys can link this work to what's going on in the river, it's a gravy train for money. Yeah.
Yeah.
In Delaware here, we have Robert Beach, Bethany, Kenwood Island. Do we consider those barrier islands?
I'm actually not sure.
Yeah.
I think so, yeah.
Very important.
Yeah, there's a lot on these.
Armando, actually, you've really focused on St. Vincent, but what can you say about St. George? I mean, do your results apply to St. George as well?
It's hard to tell because in 2015, because of our sampling protocol, we didn't have any recaptures. So it's really hard to say. So
There are freshwater wetlands on
there are freshwater wetlands. So I would say that it does apply to St. George Island as well.
So your assessment of, St. Vincent Island being an important stopover site for primarily watercress, I guess, does that apply also to St. George? That's what I'm asking.
Sure, I think they have similar habitats. I think you can't really say that because they're drastically different islands. And if we had recaptures and we could assess whether they gain mass in these things, we could say that. But because in 2016 we only focused on St. Vincent Island, and I think our sampling protocol in 2015 from 3 days on, 3 days off, that really inhibited our ability to recapture birds, right? Because we're off the island for 3 days. So I can't necessarily say that. I would hypothesize that it would be similar if we had recaptured to say that way. Yeah.
So we should be interested in also protecting or managing wisely freshwater wetlands on St. George.
Yeah.
As well as St. Vincent.
Yeah, and I think as a system, we should think about it as Apalachicola Bay in general. So just the whole system, which is the river, which are these islands, which is the water, the salinity levels. I think we should, look at all of this because something that's in St. George Island might affect what's going on in St. Vincent Island, and what's going on upriver is going to affect everything. So we have to think of it as a whole system. But yeah, I think what I found in St. Vincent could be applied to St. George. That's what I think.
Okay. All right, thanks, Armando.
All right, thank you.